Let's move for the final presentation of the morning session. This presentation will be performed by Francesco Bencardino. It's about externally applied textile reinforced systems. Francesco Bencardino is Associate Professor in Structural Engineering at the University of Calabria, Department of Civil Engineering. His main research topic is innovative materials and techniques for strengthening and repair of existing reinforced concrete and masonry structures. Francesco is a member of some FIB and CNR task groups. He's author of over 50 scientific papers with about 1,400 citation and a H index of 20. So please, Francesco, whenever you are ready, you can start your presentation.
Thank you, Eduardo. I'm going to speak about externally applied textile reinforced systems, chapter 6 of the FIB bulletin. Specifically, this is a contribution on the following topics: innovative materials, systems, and techniques for strengthening and repair of existing reinforced concrete structures, sustainable aspects of the interventions in terms of materials, execution, and maintenance, details about the quality control of the strengthening system and technique. Generally, the existing RC structures that need to be strengthened are also deteriorated. Cover concrete detached, internal steel bars reinforcement corroded, and so on. These are some examples: column, joint, spalling of the cover concrete, corrosion of internal steel bars reinforcement in slab, truss, and beams. Some examples of concrete surface conditions: carbonation, cracks, chloride, and so on. A solution could be the use of composite materials. Composite materials with organic or inorganic matrix. In the case of organic matrix, we have the fiber reinforced polymer FRP system, fibers with epoxy resin. In the case of inorganic matrix, we have the textile reinforced mortar or textile reinforced system in general, fibers with mortar, mortar based on Portland cement in the case of RC structures, mortar lime-based in the case of masonry structures. This is a list of alternative names used for inorganic composed systems for strengthening RC structures. Generally, they can be called textile reinforced system. The typical fabrics used for TR systems are carbon, steel, PBO, basalt, glass, uni or bidirectional. Carbon, steel, and PBO are suitable for RC structure members. The matrix used for TR system is made of a combination of Portland cement, silica fume, slag, fly ash, and other. Different solutions were proposed. Matrix based on cementitious, lime, polymer, natural mineral, alkali activated materials, and geopolymeric matrix. The alkali activated materials and geopolymers used as matrix and steel carbon PBO fibers in steep tape fabric and mesh format have recently been proposed as a green technology with sustainable aspects. This is the textile reinforced system or FRCM system. These are some examples of matrices available in the market. Beton fixed monolite N, beton fixed monolite R, geolite. Each of them is a mortar suitable for structural strengthening and repair, corrosion protection of the steel bars, protective coating or surface protection of the concrete, The mortar is certified according to the European standards. In conclusion, the textile reinforced systems are an alternative to traditional systems and techniques, such as steel plate bonding, section widening, external post-tensioning, and fiber reinforced polymers. This is a list of advantages of the textile reinforced system. A textile reinforced system can be applied according to different techniques. According to the traditional technique, EB, externally bonded technique, or innovative technique, the IRS technique, inhibiting, repairing, strengthening. In this case, the matrix also provides corrosion protection of the internal steel bars. It contains slag, fly ash, and can be classified as an alkali activated material or geopolymeric matrix. A green technology. The difference between EB and IRS technique is shown in this slab. According to the EB technique, the following steps should be carried out. Step 0, removing of deteriorated concrete, cleaning and of corroded steel bars. Step 1, protection of corroded steel bars. Step 2, restoring of concrete substrate, restore the shape of the structural member. Step 3, application of external reinforcement system. According to the IRS technique, the step 0 is the same for both techniques, but the 3 steps, 1, 2, and 3, can be performed with 1 step. 3 steps in 1 step. Reduction of time, cost, and pollution. It's an innovative solution. It's a sustainable solution. This is an example of the strengthening procedure according to the externally bonded technique. 0, removal of deteriorated concrete and cleaning of corroded steel bars. 1, application of corrosion inhibitor, corrosion protection of the steel bars. 2, restoring and repairing of concrete, restore the shape of the structural member. 3, strengthening system application, strengthening completed and finishing touch. In summary, surface preparation in steps 0, 1, and 2, and strengthening application, step 3. According to the IRS technique, the steps 1, 2, and 3 can be performed in 1 step. These are the operations for the EB technique listed in the FIB document. This figure is a sketch of the EB technique. These are the operations for the IRS technique listed in the FIB document. The IRS technique uses an inorganic matrix, which also acts as a corrosion inhibitor. It's very important. This figure shows a sketch of the IRS technique. These are the operations for the near surface mounted technique. This technique uses a traditional inorganic matrix, not a geopolymeric matrix. This is a sketch of the NSM technique. The IRS and NSM techniques are similar. The main difference between them is in the type of matrix used to apply the fibers. IRS uses geopolymeric matrix. NSM uses traditional inorganic matrix. These are some examples of in-field application. Flexural strengthening over slabs, strengthening of a railway bridge, confinement of column, strengthening of a receive beam column joint. Well, in this slide, we can see the people involved in the strengthening and repair process and its role. The owner should provide the sources for the acquisition of the necessary data. The assessment of the structural geometry, structural details, and material properties are necessary in order to achieve a knowledge level to which a specific confidence factor should be adopted according to national or international guidelines. Designer must have data of the mechanical properties of the innovative materials technical data sheet. The designer must be aware already in the planning phase that the composite systems that will be used in a strengthening project will have to be identified and qualified. The contractor must be demonstrate ability in surface preparation and textile reinforced system installation. The user, in the years after the strengthening intervention, should provide a series of maintenance interventions in order to avoid the development of a possible critical situation that put the safety of the work at risk. This is a general procedure for repair and strengthening of existing RC structures. The listed main steps are performed with some differences if the TR system is applied according to EB, NSM, or IRS techniques, as seen previously. In this part, we can see the quality control for each strengthening system with different weight per unit area, nets and matrices, binder and any additives. Tests must be performed and the results must be recorded. The initial tests that must be performed for system qualification are mechanical and durability tests, specifically tensile test on dry fibers and a single lap shear test for the mechanical characterization. Construction supervisor, duty and function. Before intervention, the construction supervisor must verify that the strengthening system that arrives in situ has a certification that identifies its performance characteristics. During intervention, the construction supervisor must verify that the installation procedure is observed with particular regard to the correct mixing and dosage of the components and to the correct application of the TR system. After intervention, the construction supervisor is responsible for performing in situ acceptance checks. These checks are mandatory and must be performed on samples made together with the installation of the TR system using the same materials and in the same in situ conditions. The samples should be at least 6 for each type of TR system. 3 of the 6 samples must be produced and sent to a laboratory in order to perform the tensile test. The samples must have the following characteristics: rectangular cross-section, width at least 4 times the grid spacing, length between 4 and 15 times the width. The nominal thickness is indicated on the technical data sheet. On the other 3 samples of TR system, single lap shear test must be performed using in situ proofs. Where this is not possible, it's necessary to prepare concrete prisms to carry out the tests. Details of the specimens are listed here length and width of the fabric, dimensions of the concrete prisms, and so on. After the test, we have the following data. From tensile test, the ultimate tensile load for each sample, and knowing the cross-section area of the fibers, we can evaluate the average value of the tensile ultimate loads and the average value of the ultimate tensile strength, sigma UM. From the single lap shear test, we have the maximum detachment force for each sample, and the average value of the maximum detachment force can be calculated, F max M. From the technical data sheet, the following data are given. Ultimate characteristic tensile strength, Young's modulus of the fibers, cross-section area of the fibers, and the conventional limit strain. The conventional force limit can be calculated using the following relationships. F max convention. The acceptance test is positive if both check 1 and check 2 are satisfied. Check 1, the average value of the ultimate tensile strength is not less than 85% of the ultimate characteristic tensile strength of the TR system provided on the technical data sheet. Check 2, the average value of the maximum force that can be transferred to the support is at least 85% of the conventional limit value provided on the technical data sheet or calculated by the data in the technical data sheet. If the results are negative for at least one of the two checks, additional samples of textile reinforced system, 3 for each negative test types, must be produced, and the same procedure must be performed. The acceptance test is positive if both evaluated on 6 samples are satisfied. In the event of further negative results, the textile reinforced system package must be considered not in compliance with the technical data sheet. Monitoring and maintenance. Designer, at the end of the textile reinforced system installation, provides an inspection plan and a maintenance plan. Inspection should be periodically performed. It's important to understand the factors that can damage the textile reinforced system. This allows intervening and solving the problem. It's necessary to perform a visual inspection to observe if the bonding, cracking, and deflections and other anomalies exist. Well, now we are going to show some case studies, 4 case studies. Case study 1. In this case, the TR system is steel fibers, are steel fibers with inorganic matrix, specifically UHTSS fibers, geosteel, with inorganic matrix, geolite. We can see the confinement and the flexural reinforcement of columns. First layer of mortar, application of geosteel, second layer of mortar, particular of in anchorage. Confinement of a node, application of geosteel in the beam, second layer of mortar. Shear reinforcement and anchorages with injector and connector. Bending reinforcement, first layer of mortar, application of geosteel in second layer of mortar, strengthened beam at left and unstrengthened beam on the right. Strengthened beam, unstrengthened beam. Okay. This is a sketch of the external reinforcement system. Confinement and flexor reinforcement of a column, confinement of a node, shear and bending reinforcement in the beams. Case study 2. This is a PBO system. PBO fibers embedded in a cementitious mortar. We can see the building before the intervention, a view of the RC frame, a survey of the slab reinforcements. Some beams were cut and tested in the laboratory. We can see the cut of the RC beams, handling of a beam, test setup of the strengthened beams, failure mode of the tested strengthened beam. The results of this experimental investigation were used to design the strengthening intervention. This is a strengthening scheme for beams and columns, and this is the application of the PBO fabric on the first matrix layer and the application of the second matrix layer. Case study 3. This is a carbon system, high resistance carbon mesh embedded in a shotcrete matrix. This is a view of the water tank before the intervention. This is the strengthening scheme for the walls and detail of the connection between exterior wall, party wall, and exterior walls between them. Removal of the obsolete components, concrete injection, preparation of the surface by hydroblasting. First layer of the matrix shotcrete, installation of the carbon mesh, second layer of the matrix. This is a view of the connection between walls, a cross-section of the new filters, and view of the complete installation of the new filters, further details, and final aspect of the intervention. The last case study 4. This is a system, a textile system made by stainless steel and inorganic matrix. We can see the condition of the column and steel corrosion and cover concrete degradation. Cleaning of the steel bars and application of the passivating mortar on the steel rods. Here we can see the cover concrete restoring, volumetric reconstruction of the concrete, restore the shape of the structural member, application of the longitudinal stainless steel strips, longitudinal and transverse stainless steel strips, further step, application of the second layer of the matrix. I'm going to conclude. This is a list of the main references. The CNR document is a useful guide for design and construction of externally bonded fiber reinforced inorganic matrix systems for strengthening existing structures. It is a good document to design a textile reinforced system, as shown before. Okay, thanks for your kind attention.
Thank you, Francesco. It was a very nice and well depicted presentation. So let me check the Q&A button. So it seems that we don't have questions. However, I can...
Very well. There's no problem.
Maybe if someone from the audience wants to raise your hand and directly speak with Francesco. Oh, wait. It seems that we have a question. It's from João Firmo, and he says, since TRM is a relatively new technology, in your opinion, what are the main topics that still need to be investigated in further depth?
Okay, very good, very good questions. It's important to define the strain, the maximum strain that we can have in the textile reinforced system that we use. And it's necessary to have some data in the technical data sheet. This data refers to and the bonding, okay? But in many cases, we have the intermediate debonding, and this value is very important to calibrate the strengthening interventions. And this value is different in the case we use steel, PBO, or carbon. And it's vary also with the same fibers, in example, the steel fibers, when we change the grammage, 600 or 800 or 1000. This is a topic under investigation. This is an experimental field.
Okay, thank you. So it seems that we have more questions now. Another one from Felipe Dourado. What is the required bonding between FRCM and the grid to activate a reasonable force on the composite?
There is not a suitable value because in existing RC structure, we have different value of the concrete surfaces, okay? Low strength, medium strength, or high strength. It's depend of the textile system that I think to use, because in the technical data sheet, we have the data of the surface strength on the support. It's clear?
Well, for me, yes. I don't know if for Philippe, but if Philippe can put a different question or chat directly with you to if the question, if you'll not feel satisfied with your answer. I will move to the next question. Now it's from Gassan Hashem. How to decide between FRP and TRM, for example, for axial enhancement of columns?
It's a very interesting question. There is not a single parameter to decide if I want to use FRP system or FRCM system. In many cases, in the case of fire resistance, it's preferred to use the FRCM system or textile reinforced system with a cementitious mortar. In the case of confinement of columns, in many cases, the FRP system is more performant. It's better compared to the textile reinforced system using the steel fibers. But I can apply also a pretensioning in the steel fibers. And in this case, the confinement effect is better. It's better in the textile reinforced system that use the steel fibers, for example. Okay?
Okay. So we don't have any more questions. So I would like to thank you again, Francesco, for your nice presentation, very well depicted with many different case studies. So it was a pleasure to assist to your presentation. Thank you.
Thank you very much. Thank you.